In the present video, I will explain the how to solve the LP problem by BTech method. Let's see the problem. Use penalty method to solve the following LP problem. Minimize z equal to 12x1 plus 20x2 subject to the constraints 6x1 plus 8x2 greater than or equal to 100, 7x1 plus 12x2 greater than or equal to 120 and x1, x2 are greater than or equal to 0. Let's see the solution. First observe the given problem is maximization or minimization model. Here given problem is a minimization model. Then we have to convert the minimization model into maximization by multiplying the objective function with -1. Then objective function, that is minimize z equal to 12x1 plus 20x2 become maximize z equal to minus 12x1 minus 20x2. Next step is convert the general linear programming problem into standard linear programming problem. In BTech method, any constraint having less than or equal to inequality symbol, then add a slack variable, that is plus s. If any constraint having greater than or equal to inequality symbol, then subtract a surplus variable and also add a artificial variable, that is minus s plus a. Similarly, if any constraint having equal to symbol, then add an artificial variable, that is plus a. In a given LP problem, first constraint having greater than or equal to symbol, then subtract a surplus variable s1 and add a artificial variable a1. Then the first constraint become 6x1 plus 8x2 minus s1 plus a1 equal to 100. Second constraint also having the greater than or equal to symbol, then subtract surplus variable s2 and add artificial variable a2. Then the second constraint becomes the 7x1 plus 12x2 minus s2 plus a2 equal to 120. Then write the objective function in the terms of the decision variables x1, x2 and surplus variables s1, s2 and artificial variables a1 and a2. Now objective function is the maximize z equal to minus 12x1 minus 20x2 plus 0s1 plus 0s2 minus m a1 minus m a2 and x1, x2, s1, s2, a1, a2 are the greater than or equal to 0. Here 0 is the cost coefficient for the surplus variables and minus m is the cost coefficient for the artificial variables. Second step is find the initial basic feasible solution. For this, we have to consider the decision variables and the surplus variables are 0. Here decision variables are the x1, x2 and surplus variables are the s1, s2. So here we have to consider the for initial basic feasible solution x1, x2, s1, s2 are considering 0 and substitute in the constraint equation. We will get the a1 value is the 100 and a2 value is the 120. Next step is construct the initial simplex table. This is the initial simplex table. Here B is the basic variables. Here we are considering the a1 and a2 are the basic variables. Then I have to enter the a1 and a2 values in the column B. And CB is the cost coefficients of the basic variables, that is minus m is the coefficient for the artificial variable a1. Similarly, minus m is the cost coefficient for the artificial variable a2. Then you have to enter the minus m and minus m in the CB column. Next, xb is the initial basic feasible solution, that is 100 and 120. Next, to write the coefficient of variable values here. For this, observe the constraint equations. First, we have to observe the first constraint equation, that is 6x1 plus 8x2 minus s1 plus a1 equal to 100. Here 6 is the coefficient for the x1 and 8 is the coefficient for the x2, minus 1 is the coefficient for the s1. So here there is no s2. So s2 coefficient is the 0 and 1 is the coefficient for the a1, and here there is no a2. So a2 coefficient is the 0. Next, observe the second constraint equation, that is 7x1 plus 12x2 minus s2 plus a2 equal to 120, and we have to write the coefficients of the variables, that is 7, 12, 0, minus 1, 0 and 1. So next we have to write the Cj values. Here Cj is the cost coefficients of the variables. For this we have to observe the objective function, and x1 coefficient is the minus 12. So I have to enter here minus 12, and x2 coefficient is the minus 20, and s1 coefficient is the 0, and s2 coefficient is 0, a1 coefficient is the minus m, and a2 coefficient is the minus m. Next step is calculate the Zj minus Cj values and check the basic feasible solution for optimality. If all the Zj minus Cj values are greater than or equal to 0, then optimal solution will be obtained. If at least one Zj minus Cj is the negative, then indicated by arrow, this column is called as the key column. If more than one Zj minus Cj is the negative values, then choose the most negative of them, and respected column is called as the key column. So first we have to calculate the Zj minus Cj values for all the variables. Here Zj is the summation of multiplication of Cb and Xj. So first to calculate the Zj minus Cj for the x1 variable, which is the Z1 minus C1. So Z1 minus C1 is the minus m into 6 plus minus m into 7 minus of 12. So it is the minus 6m plus minus 7m plus 12. So it is the 13m plus 12. Next, to calculate the Zj minus Cj value for the x2 variable, that is the Z2 minus C2, which is minus m into 8 plus minus m into 12 minus of minus 20. So which is equal to the minus 20m plus 20. Next, to calculate the Zj minus Cj for the S1 variable, that is Z3 minus C3, which is the minus m into minus 1 plus minus m into 0 minus of 0, which is equal to the m. Next, to calculate the Z4 minus C4 for the S2 variable, which is the minus m into 0 plus minus m into minus 1 minus of 0, which is equal to the m. Next, to calculate the Z5 minus C5 for the A1 variable, which is equal to the minus m into 1 plus minus m into 0 minus minus of m, which is equal to the 0. Similarly, we have to calculate the Z6 minus C6 for the A2 variable, which is equal to the minus m into 0 plus minus m into 1 minus of minus m, which is equal to the 0. So among these values, here negative values are the minus m plus 12 and minus 20m plus 20. So in these two negative values, we have to select the most negative value, that is the minus 20m plus 20 for the x2 variable. So x2 variable column we are calling as the key column, and x2 variable we are calling as the incoming variable, which is x2 variable enter the basis. Next step is calculate the minimum ratio of the xb divided by coefficient of incoming variables. Here x2 is the incoming variable. So first to calculate the ratio of xp divided by coefficients of incoming variable for the first row. So for the first row, xb value is the 100 and coefficient of the incoming variable is the 8, then 100 by 8. So next we have to calculate the minimum ratio of the xp divided by coefficient of the incoming variable for the second row. Here xp value is the 120 and coefficient value is the 12. So 120 by 12, which is equal to the 10. So among these two values, minimum ratio is the 10. So that is for the second row, which having the in the basis A2 variable. So minimum A ratio is the 10 and indicating by the arrow, and the A2 is calling as the outgoing vector, which means in the basis variable A2 leaves the basis. So here x2 is the incoming variable and A2 is the outgoing variable. So next step is we have to identify the common element in the key row and the key column. Here key row is the A2 variable row. So this is the key row, and key column x2 variable column is the key column. This is the key column. Among these two, key column and key row, common element is the 12. So 12 we are calling as the key element. Next step is we have to construct the new simplex table by entering the incoming variable as x2. We construct a new simplex table with reference from the old simplex table. In new simplex table, we have to replace the A2 variable by x2 variable. So in new simplex table, enter x2 variable in the basis and enter its coefficient value as the minus 20 in the CB. Next, Cj values are the same as the in the old simplex table, that is x1 cost coefficient is the minus 12, x2 cost coefficient is the minus 20, s1 cost coefficient is the 0, s2 cost coefficient is the 0, a1 cost coefficient is the minus m. Here we are removing the A2 column in new simplex table because here A2 variable is outgoing variable. Next we have to modify the xb value and all variable coefficient values by the following row operations, that is R2 new equal to R2 old divided by key element. Here key element is the 12. So R2 new equal to R2 old divided by 12, and the second row operation is the R1 new equal to R1 old minus 8 R2 new. Here R1 old is the first row in the old simplex table and R2 old is the second row in the old simplex table. R1 new is the first row in the new simplex table and R2 new is the second row in the new simplex table. First we have to look for the first row operation, that is R2 new equal to R2 old divided by key element. Here key element is the 12. So first we have to write the old element in the R2, that is the 120, 7, 12, 0, minus 1, 0. Then divided by 12, it is the R2 new. So 120 by 12, it is the 10. And 7 by 12, it is the 7 by 12. And 12 by 12, it is the 1. 0 by 12, it is the 0. Minus 1 by 12, it is the minus 1 by 12. 0 by 12, here 0. Then enter these values in the second row of the new simplex table. Next we have to look for the second row operation, that is R1 new equal to R1 old minus 8 R2 new. So first to write down the R1 old element, that is the 100, 6, 8, minus 1, 0, 1. Similarly I have to write down the R2 new values, that is 10, 7 by 12, 1, 0, minus 1 by 2. Next we have to do the 8 into R2 new, that is 8 into 10, 80, 8 into 7 by 12, 56 by 12, 8 into 1, 8, and 0 into 8, 8, minus 1 by 2 into 8, that is minus 8 by 12, and 0 into 8, that is the 8. Next, R1 new is the R1 old minus 8 R2, which means 100 minus 80, which is the 20, 6 minus 56 by 12, that is 16 by 12, 8 minus 8, 0, minus 1 by 0, minus 1 minus 0, that is the minus 1, 0 minus 8 by 12, which is the 8 by 12, 1 minus 0, 0. Enter these values in the R1 new. Next to calculate the Zj minus Cj values and to check the basic feasible solution for optimality. So first we have to calculate the Zj minus Cj for the x1 variable, which is Z1 minus C1 equal to the minus m into 4 by 3 plus minus 20 into 7 by 12 minus of minus 12, which is equal to the minus 4m by 3 plus 1 by 3. Next for the x2 variable, that is Z2 minus C2 equal to the minus m into 0 plus minus 20 into 1 minus of minus 20, which is equal to the 0. Next Z3 minus C3 for the S1 variable, minus m into minus 1 plus minus 20 into 0 minus 0, which is equal to the m. Next for the S2 variable, which is equal to the minus m into 2 by 3 plus minus 20 into minus 1 by 12 minus 0, which is equal to the minus 2m by 3 plus 20 by 12. Next for A1 variable, which is equal to the minus m into 1 plus minus 20 into 0 minus of minus m, which is equal to the 0. So among these Zj minus Cj values, most negative value is the minus 4m by 3 plus 1 by 3 for the x1 column. So here x1 column is the key column and calling as a incoming vector, and x1 variable is the enters into the basis. Next to calculate the minimum ratio of xb divided by coefficient of incoming variable values. So first we have to calculate the ratio of xb divided by coefficient of incoming variable value for the first row. In the first row, xb value is the 20 and incoming variable value is the 4 by 3. So the ratio of the 20 divided by 4 by 3, which is equal to the 15. Similarly, we have to calculate the ratio of xp divided by coefficient value of the incoming variable, that is 10 divided by 7 by 12, which is equal to the 17.14. So among these two values, minimum ratio is the 15 and it is indicated by the arrow, and A1 is the outgoing vector. So here minimum value is the 15 for the first row. In the first row, so A1 is there in the basis. So A1 is outgoing vector. So basic variable A1 leaves the basis. So next we have to identify the common element in the key row as well as the key column. Here key row is the A1 variable row and key column is the x1 variable column. Among these two, key row and key column, common element is the 4 by 3. So here 4 by 3 is the key element. Next we have to construct the new simplex table by entering the incoming vector as x1 for the second iteration. So next we have to write a new simplex table with the reference of the old simplex table of the first iteration table. So here, so most negative value z1 minus c1 for the x1. So here x1 is chosen to replace the basic variable a1 in the basis. So I have to replace the a1 by the x1 and also have to replace is to cost coefficient value. So x1 cost coefficient value is the minus 12. So enter the minus 12 in the CV. So next we have to Cj values. So Cj values are the cost coefficient values. So that is the for the x1 variable minus 12, x2 is the minus 20, s1 is 0 and s2 is 0. Next we have to remove the a1 column in the new simplex table. Next we have to modify the xb values as well as the variables coefficient values by the following row operations, that is r1 new equal to r1 volt divided by key element. Here key element is the 4 by 3, which means r1 new equal to the r1 volt into 3 by 4, and the second row operation is the r2 new equal to r2 volt minus 7 by 12 r1 new. So first I have to look for the first row operation, that is r1 new equal to the r1 volt into 3 by 4. First I have to write down the r1 volt. So in the r1 volt elements are the 20, 4 by 3, 0, minus 1 and 2 by 3. Then I have to multiply with the 3 by 4, which comes the r1 new, that is 20 into 3 by 4, 15. So 4 by 3 into 3 by 4, 1, 0 into 3 by 4, 0, minus 1 into 3 by 4, minus 3 by 4, 2 by 3 into 3 by 4, so 1 by 4. So enter these values in the r1 new. Next we have to look for the second row operation, that is the r2 new equal to r2 volt minus 7 by 12 into r1 new. First I have to write down the r2 volt elements. So here r2 row volt elements are the 10, 7 by 12, 1, 0, minus 1 by 2, and r1 new elements are the 15, 1, 0, minus 3 by 4 and 1 by 2. Next we have to multiply this one r1 new elements with the 7 by 12, that is 15 into 7 by 12, 105 by 12, 1 into 7 by 12, 7 by 12, 0 into 7 by 12, 0, minus 3 by 4 into 7 by 12, that is minus 21 by 48, and 1 by 2 into 7 by 12, which is the 7 by 24. Next we have to perform the operation r2 volt minus 7 by 12 r1 new, which is equal to the 10 minus 105 divided by 12, which come the 15 by 12. 7 by 12 minus 7 by 12, 0. And 1 minus 0, 1. 0 minus of minus 21 by 48, 21 by 48. Minus 1 by 12 minus 7 by 24, which is equal to the minus 9 by 4. So enter these values in the R2 new. So next we have to calculate the Zj minus Cj values and to check the basic feasible solution for the optimality. So first we have to calculate the Zj minus Cj for the first basic variable for x1, that is Z1 minus C1 equal to the minus 12 into 1 plus minus 20 into 0 minus of minus 12, which is equal to the 0. Next Z2 minus C2 equal to the minus 12 into 0 plus minus 20 into 1 minus of minus 20, which is equal to the 0. And next one is the Z3 minus C3 for the S1 variable, which is equal to the minus 12 into 3 minus 3 by 4 plus minus 20 into 7 by 16 minus 0, which is equal to the 1 by 4. And next one is the Z4 minus C4 for the S2 variable, which is equal to the minus 12 into 1 by 12 plus minus 20 into minus, so 19 by 4, which is equal to the 3 by 2. So here you have to look for the all the Zj minus Cj values are the positive values. Moreover, you have to look for the in the basis. In the basis, all the artificial variables a1 and a2 have been removed. Then we got the optimal solution. So we get the optimal solution at the x1 value is the 15 and x2 value is the 5 by 4. Then I have to substitute this x1 value and x2 value in the objective function, that is maximize z equal to minus 12x1 minus 20x2, which will become the minus 12 into 15 minus 20 into 5 by 4, which is equal to the minus 205. But our original objective is minimize the z. So for this one we have to convert it maximize by with the multiplication of minus 1. Then once again we have to multiply the maximize z equal to minus 205 into the minimize z by the multiplication of minus 1. Then it is the solution is minimize z equal to minus 1 into minus 205. It is the 205. So optimal solution is the 205. Thank you.